The Carnot cycle is an ideal cycle, where all processes are reversible, and the efficiency is maximum. In reality, it's very difficult to create a Carnot cycle, as many problems will arise in running such an engine. For example, one problem is that when the steam is run through a turbine, from 2 to 3, the output of the turbine is wet steam, which is a mixture of water and steam. As a result, this will cause corrosion in the turbine parts, and will create further problems. Another problem is that the input to the compressor or pump, at state 4, is also wet steam. Compressing such a mixture is very difficult and takes up a lot of energy, which will reduce the total efficiency of our engine. To solve all these problems, a new cycle was introduced by a Scottish engineer, William Rankine, which is called the Rankine cycle. He made many changes to the design of the old vapor power cycle engines. First, he decided to superheat the steam, which moved point 2 further right. By doing so, the steam at point 3 was less wet, or had a higher dryness fraction. As a result, the turbine's corrosion was eliminated. Secondly, he decided that the condensation process would occur until the steam became saturated liquid. By doing so, it became much easier for the compressor to do its work, since it only had to compress liquid, not a mixture of liquid and gas. Lastly, he changed process 1 to 2 from an isothermal process to an isobaric process. This way, the pump had to do much less work to reach the required temperature. The temperature would be reached on its own when the water became saturated. Since the input to the pump is now saturated liquid, it cannot be compressed, and hence the volume remains constant, while the pressure increases. So on the PV diagram, the curved line from 4 to 1 becomes a vertical straight line for constant volume. So altogether, the 4 processes are isobaric expansion from 1 to 2, adiabatic expansion from 2 to 3, isobaric compression from 3 to 4, and adiabatic compression from 4 to 1. For each of these 4 processes, there is a dedicated machine. For isobaric expansion from 1 to 2, we use a boiler, which provides heat input. For adiabatic expansion from 2 to 3, we use a turbine, which extracts work. For isobaric compression from 3 to 4, we use a condenser, which removes heat. And for adiabatic compression from 4 to 1, we use a pump, or compressor, which takes in work. Using the HS diagram, we can calculate the heat and work transfer in each process, using the change in specific enthalpy. For the pump, however, we usually calculate the work done as specific volume times the change in pressure, since the enthalpy of subcooled liquid is difficult to find. Now, the thermal efficiency is desired output by the input given. Here, the desired output is to have some net work done, and the input given is heat from the boiler. We can calculate the net work done as the difference between the work extracted by the turbine and the work taken up by the pump. Substituting the enthalpy values, we can rearrange the terms in order to get the result. Thermal efficiency is equal to 1 minus H3 minus H4 by H2 minus H1. This is the efficiency of a Rankine cycle. Sometimes we make the consideration that work done by the pump is too small to be included. In that case, we calculate the efficiency as work done by the turbine divided by heat input from boiler. Or in enthalpy terms, H2 minus H3 by H2 minus H1. So depending on the situation, we have to use the appropriate equation and substitute the values of enthalpy using the information given.